What?
The blood flow equation, you know, at the top it's pressure. Is that?
Oh yeah, that difference in pressure. Yeah. Well, yeah, we don't really talk about it in that same context, but it is a difference in pressure in that flow equation. It's not directly related here. Pulse pressure is that difference in pressure that you feel when you're counting the beats per minute for someone. Yeah. So the different pulse points of the body are going to be the superficial temporal artery, which is next to the temporalis muscle that you guys should have learned in B32. Facial artery around the chin. The common carotid is a very common pulse point around the neck. The brachial artery you're going to feel at the elbow. Radial on the outside of the wrist. Femoral is up towards the groin area. Popliteal behind the knee. Posterior tibial on the back side of the ankle, and then the dorsalis pedis on the top of the foot. Okay. So you should be familiar with those different pulse points. And they're all arteries that are on your learn lists anyway, except for the facial. Not superficial temporal either. So those ones at the top I probably wouldn't ask you about, but the ones that are on your learn list I would ask you about as far as pulse points go. All right, so vital signs. So vital signs are objective measurements of the body's essential functions. So temperature gives us a good idea of your health overall if you are fighting an infection or if there's some kind of inflammatory response going on. Pulse gives us an idea of how the heart's working. Respiratory rate as well. Blood pressure is what we're going to focus on today. And then after exam 1, when we get to the respiratory system, we'll talk about oxygen saturation, but we're not there yet. But we're going to focus on blood pressure today. So measuring blood pressure, this is most often measured indirectly by the brachial artery. So usually they put a blood pressure cuff around your arm to measure pressure there. Sometimes they'll do it at the wrist as well. So we'll be doing wrist blood pressure monitors today. I'm going to go through step by step how to take blood pressure. Now, you all don't have to do manual blood pressure readings. We actually don't have a manual pump for you guys to use. We have the digital ones here, but you should understand the mechanisms of how we take blood pressure either way. So when you're taking a manual blood pressure reading, first you're going to wrap the blood pressure cuff around the person's arm, which is called the sphygmomanometer. You're going to wrap it snugly around the person's arm just superior to the elbow, which is where the reading for the brachial artery is. You inflate the cuff until the cuff pressure exceeds systolic pressure, so you want to go well above that 120 to be able to cut off blood flow to the arm temporarily. Now, if somebody is dealing with chronic hypertension and their systolic pressure is higher than 120, you're going to have to go even higher than that in order to get that cutoff of blood flow. So at this point, blood flow into the arm stops and a brachial pulse cannot be felt or heard. So at the same time, the clinician is going to be listening for heart sounds through the stethoscope. So you want to inflate that cuff until it exceeds that systolic pressure and the blood flow is cut off, as you see at the very top. From there, you're going to gradually reduce the pressure to open up that space so that blood flow can resume. And you're going to be listening to sounds for when that happens. So you reduce the cuff pressure gradually and then listen or oscillate with a stethoscope for sounds in the brachial artery. As blood spurts through the constricted artery, soft tapping sounds called Korsakoff sounds can be heard. So as you're reducing the pressure and you're kind of opening up that tightness around the blood vessel, once you open up that blood vessel just a little bit, you're just going to hear sounds of just blood spurting through first. It's not going to be a continuous flow. It's why you have to gradually kind of reduce that pressure until you start hearing the tapping sounds of blood being kind of squirted through. You're going to record the pressure in millimeters of mercury when the first sound is heard. That first sound is the systolic pressure. It's when the pressure in the cuff is equal to or slightly lower than the pressure in that vessel. That's when it's going to be equal to what's at the heart. And so when you hear that first sound, that's going to be your systolic pressure. Okay. Everyone okay with that? Okay. So Again, as you're just barely opening up that blood vessel and resuming blood flow, again, that blood is kind of squirting through as it's trying to get through that passageway. But eventually, as you open up that vessel more and more and reduce that pressure, you won't be able to hear a sound at all. Remember we said before, blood flow is super continuous and super smooth, and so you don't hear differences in blood flow. You shouldn't, unless there's a problem. And so once we open up that vessel all the way, those sounds should disappear. And now we've resumed with continuous blood flow. So sounds will disappear when the artery is no longer constricted and blood flows freely. So once you stop hearing those tapping sounds, that's when you record pressure again, and that will be your diastolic pressure. Everyone okay with that? Okay. So where is blood pressure going to be highest? It's going to be highest in the aorta, where we're closest to the heart. As you get further away, arteries is going to be slightly lower, arterioles even lower than that, capillaries, venules, veins, and like I said, vena cava are going to be essentially at 0 millimeters of mercury. What is the average blood pressure? 120 over 80. So make sure you remember that. So blood pressure is controlled or regulated by short-term and long-term controls. So this is a diagram showing how to increase mean arterial pressure. Mean arterial pressure is essentially your blood pressure. And so ways that we can increase blood pressure, if you increase either stroke volume, so if you have an increase in contractility, you're going to increase cardiac output, which increases your blood pressure. Also, if you increase heart rate, if you're in fight or flight mode and your heart is beating faster, then you're going to have a higher cardiac output and therefore a higher blood pressure. You just did a PLA on blood flow and resistance. You should have wrote down the 3 different factors that are going to change peripheral resistance or influence peripheral resistance. How we increase it though, is when you have a lower diameter of the blood vessels. We talked about the boba straw versus a coffee straw. If you lower or decrease the diameter of any blood vessel, you're going to increase the resistance to blood flow. It's going to be harder for blood to flow in a smaller blood vessel. Also, if you increase blood viscosity, so if your blood is thicker than it normally is, and that is also going to be resistant to blood flow. It's much easier to drink water than it is to drink a smoothie that's thicker, right? And so if you increase blood viscosity, which you can if you have lower levels of oxygen detected, so we talked about that feedback mechanism with EPO. So let's say you go up to Colorado in the mountains and you're not used to that. Your body is going to detect that lower pressure from being up at a higher altitude. Your kidneys will produce EPO. You'll produce more red blood cells than you normally do. Your blood will be thicker, and that will cause a resistance to blood flow. Also, if you have an increased blood vessel length, so people who are taller in general have a higher resistance to blood flow just because their heart has to work harder to get that blood a farther distance. It's much easier to travel from point A to point B when this is the distance than it is to travel from point A to point B, when it's a much longer distance. So those people who are abnormally tall tend to have heart issues later in life because of that strain on the heart from having to pump for a farther distance. So any questions about that? And anytime you increase resistance, you're increasing blood pressure. Yes?
So being in a higher altitude in general, raise your blood pressure?
Yes. Yes. Unless if you're born in higher altitudes, then your body's going to adapt to that over time and it'll regulate itself. But yeah, if you go to a higher altitude, yes, you'll have your body's going to try to compensate for that lower levels of oxygen. And yeah, your blood pressure will increase for sure. All right. So more about the autonomic nervous system. This is going to be short-term regulation of blood pressure. When you have increased sympathetic activation, so you're in fight or flight mode, you've experienced something exciting or embarrassing or scary, what have you, what's going to happen is you're going to have an increased heart rate, which is going to increase cardiac output. Remember that your sympathetic nervous system has connections on the SA and AV node. At those locations, the epinephrine and norepinephrine, or the catecholamines, are going to be making those cells there, the pacemaker cells, depolarize faster. And so then you're going to have a faster heart rate, which is going to increase cardiac output. Sympathetic nervous system also has connections on the ventricles of the heart at the myocardium. When the catecholamines are released there, it increases contractility of those ventricles, which is also going to increase cardiac output. When you increase contractility, which factor in cardiac output are you really increasing? Stroke volume. Hey, cardiac output is determined by heart rate and stroke volume. By increasing contractility, you're increasing your stroke volume, which is then going to increase cardiac output. So don't forget, cardiac output is equal to stroke volume times heart rate. Do not forget that equation. I swear, every semester we talk about this in the first unit. I ask you that same question in the final exam, and so many people forget. What are those acronyms? What are those things? Don't forget it. Tattoo it on your arm. Do what you gotta do. So,
Considered cheating?
huh?
Would that be considered?
That would be. I mean, if you had an actual tattoo with the card, I mean, what can I do? Make you put a Band-Aid over it or something? Okay, it's funny because sometimes I'll wear a shirt that has to do with the exams, and I'll see people like looking much more closely at the shirt that I'm wearing, like if it's a heart labeled or what, and they're like. So anytime you increase cardiac output, you're going to have an increase in blood pressure overall. Okay. Parasympathetic nervous system, if your rest and digest is activated, then you're going to have less of a heart rate, a slower heart rate, which is going to decrease cardiac output. And this time it's because of acetylcholine being put on the SA and AV node, making them work slower, depolarize at a slower rate. And then also, even though the parasympathetic nervous system does not have connections at the ventricles, when we have parasympathetic activation, that means less catecholamines on the heart. So indirectly, we're going to have a lower contractility, which is going to lower cardiac output. And it's not directly because of acetylcholine, but it's because of the lack of the catecholamines at that time. Does that make sense? Okay. And so those will, anytime you decrease cardiac output, you're going to decrease pressure overall. And remember, this is autonomic control from the autonomic nervous system. What are the effectors for the autonomic nervous system? Cardiac muscle is one, glands is another. What's the last one? Smooth muscle. In this case, we're talking about the smooth muscle of our blood vessels. What is the other system? Besides autonomic, what's the opposite system? Somatic nervous system. And what does that control? What kind of tissue does that control? Skeletal muscle. Just asking. All right, so with blood vessels specifically, if we have increased sympathetic activation, we're going to have vasoconstriction at things like our skin and our digestive organs, as well as our kidneys. Because we're going to want to bypass those areas during times of fight or flight. Okay? Because we're going to want to give that blood, redirect that blood to the heart and the brain and the lungs. So again, during sympathetic activation, we are constricting at these organs that do not need blood flow during that time. We're going to bypass those organs. And so through that, we do that through vasoconstriction. So we make the diameter smaller, especially at those arterioles where the capillary beds are, so that we can bypass blood flow to those areas. During parasympathetic activation, though, we're going to vasodilate those areas, and we're going to return blood flow to those areas. And we do that through, again, vasodilation and opening up those vessels. So just as kind of a review, going back to that diagram, we can influence blood pressure by influencing cardiac output and peripheral resistance. The changes to heart rate and contractility, this is how we regulate cardiac output. And then what we just talked about with vasoconstriction and vasodilation, this is how we regulate resistance. So we regulate cardiac output through changes in heart rate and contractility, and we regulate resistance through vasoconstriction and vasodilation. questions so far? Okay. All right, so we also have neurocontrols that alter cardiac output or resistance in order to change pressure. So we do have a cardiovascular center in the medulla oblongata. Our cardioacceleratory center, do you think this is going to increase or decrease cardiac output? Increase. Cardioacceleratory center is going to accelerate or speed up the heart. What do you think the cardioinhibitory center does to cardiac output? Decreases it. It's going to slow it down. We also have a vasomotor center that's going to alter the diameter of our blood vessels. That's also in the medulla oblongata. And so in that vasomotor center, it alters vessel resistance by either vasoconstriction or vasodilation. And so how does the cardiovascular center know what signals to send out? What are the structures that are going to be detecting changes and stimuli throughout the body? Receptors. Okay. Anybody remember what the receptors are that detect pressure? Baroreceptors is what they're called, baroreceptors. All right, so we are going to go through this negative feedback loop here. There is an empty space in your notes to draw it out. You don't have to do that now if you want to just kind of walk through this with me. But you should know this from memory. Now, am I going to have you recreate this entire diagram on an exam? Probably not. But I will ask you questions about the different parts of this feedback mechanism. So make sure that you know it well. So what happens is in this negative feedback loop with regulating cardiac output as well as resistance. The first step is the stimulus, so the change. If we have an increase in blood pressure, there's going to be baroreceptors that detect that. And we actually have baroreceptors in our carotid sinuses, so in the spaces of our carotid vessels, as well as the aortic arch. And so once the baroreceptors detect that increase in blood pressure, they're going to be stimulated, and they are going to send messages or impulses to stimulate our cardioinhibitory center. Blood pressure is too high, and so we want to slow down the heart. So we are going to stimulate or trigger our cardioinhibitory center. And both of those systems are always working at any one time, both the inhibitory center and the cardioacceleratory center. And so during this time, when blood pressure is too high, we need to stimulate the cardioinhibitory center so that we can slow down the heart. But at the same time, we are inhibiting the cardioacceleratory center. So we want to increase the work of one while decreasing the work of the other. Okay? So we want the cardioinhibitory center to be the main player at that time to be able to slow down the heart. And we're going to limit the activity of the cardioacceleratory center, if that makes sense. Okay? We don't ever turn one system off completely and turn the other one back on. It's more of a balancing game. Which one is the main player at that time? So as we stimulate the cardioinhibitory center, we're going to have less sympathetic impulses to the heart. So that's going to decrease heart rate and also decrease contractility, which is going to decrease cardiac output. And on the vasomotor side, we're going to decrease the rate of vasomotor impulses. So we're not sending messages to the vasomotor center or the blood vessels very often, which is going to allow them to relax. Okay, so this cardioinhibitory center is going to slow down the heart because there's less sympathetic impulses going to it. Same thing with the blood vessels, less impulses to the blood vessels, which is going to allow them to relax. Okay? So by relaxing the blood vessels, we decrease our resistance. Now the book is going to tell you TPR. TPR is total peripheral resistance, but I'm okay if you just say a decrease in resistance. Okay? And then again, less impulses to the heart, sympathetic impulses to the heart is going to decrease heart rate and decrease contractility, which will decrease cardiac output. So through both of these measures, by relaxing the blood vessels and slowing down the heart, that should bring our cardiac output and our resistance back to normal. And so our overall blood pressure will be back to normal. Any questions on this pathway. Yes.
Does this happen right away, or is it just whenever you don't need to have high blood pressure anymore?
Anytime your blood pressure goes out of range. So the normal blood pressure is somewhere between 110 and 130 or 100 and 140. Anytime it goes above what your body deems as a normal range, and this is going to be activated. And we're going to want to slow down the heart, relax the blood vessels to bring that blood pressure back down into its normal range. And it could be for a number of things. It could be because of your heart getting overworked or overexcited, or it could be because of damage that has occurred to the heart, or it could be for a number of different reasons. But anytime you have an increase in blood pressure above what your body deems as normal, this system will be activated. On the flip side, any questions here before we go on? On the flip side, we're going to have the opposite happen when blood pressure decreases. So when blood pressure decreases, falls below the normal range, those baroreceptors are getting less of those impulses of that change. And so they are, in this case, inhibited because the blood pressure has now dropped. So all that means is different impulses are going to be sent to the brain. So we're going to have a decrease in impulses from baroreceptors because of this low pressure, okay? And what that's going to do, this low pressure and less impulses, is going to now activate the cardioacceleratory center. Okay, there's not enough messages being sent right now. Blood pressure is too low. Let's speed up the heart and constrict these blood vessels. So less impulses from the baroreceptors activate the cardioacceleratory center. And because this is a balancing game, at that time we'll inhibit the cardioinhibitory center. We want the main player to be the acceleratory center. And so because of the lower blood pressure, the less impulses being sent to the brain, this is going to excite the heart and allow it to speed up and increase contractility. So we have more sympathetic impulses to the heart because of this drop in pressure, which is going to increase heart rate and increase contractility, which will overall increase cardiac output. At the same time, because we're activating this cardioacceleratory center as well as the vasomotor center, we're going to have the vessels now constrict. Blood pressure is too low, so we want to constrict these blood vessels to bring the blood pressure back up. Through constricting blood vessels and speeding up the heart through sympathetic activation, this should bring our cardiac output and our overall blood pressure back to normal. So any questions about that system? Blood pressure is too high. No, just really at the end of the day, it's knowing the overall workings of this system. If blood pressure is too high, we want to slow down the heart. We want to reduce its contractility, and we want to dilate the vessels in order to bring that blood pressure back down. When blood pressure is too low, we want to speed up and excite the heart, make it pump more forcefully, as well as constrict blood vessels to then bring that blood pressure back up to normal. So any questions? Okay. There's not only do we have baroreceptors for detecting pressure, we also have chemoreceptors in the aorta to detect levels of carbon dioxide, levels of oxygen, and then levels of hydrogen ions in the blood. What do hydrogen ions tell us about the blood? What does it give us a reading of? Acidity or pH, right? Now, we are going to talk more about that relationship and chemoreceptors when we get to the respiratory system. Because when we have chemoreceptors detecting levels of carbon dioxide and oxygen and pH, it's really going to send a signal to our lungs to change our breathing rate to accommodate that. So we're going to come back to this idea when we get to the respiratory system. So again, hydrogen ions are going to tell us about pH. And again, we're going to come back to this idea when we get to the respiratory system.
So will this be on any like the quiz or exam?
As far as chemoreceptors go, no, we're going to come back to it. Okay. So you may see it in your book talking about these things now, but we're not going to talk about them until we get to the respiratory system. Also, your higher brain activity will also make changes to your breathing rate and your heart rate and things like that through sympathetic activation. So if you're exercising, if you have fearful thoughts, things like that are also going to be influencing your cardiac output and your blood pressure. All right. We also have some hormonal control as well. Catecholamines from your adrenal medulla are going to vasoconstrict most vessels in order to decrease flow in these non-essential areas, like your skin, like your digestive organs, like your kidneys. And so constricting most of these vessels body-wide is going to increase your pressure overall. So overall, we'll have a net increase in blood pressure. Yes, we're going to be dilating the vessels to your brain, into your heart, into your skeletal muscle. However, overall, your blood pressure is going to go up. Even though we dilate in these few areas, we're vasoconstricting in most other areas of the body. So overall, your blood pressure increases during sympathetic activation. All right. And so this is during fight or flight. We use alpha-1 receptors to constrict vessels body-wide. And then we're going to be using beta-2 receptors to dilate the vessels in these other areas. So during sympathetic activation, we increase flow to essential areas like your coronary arteries, like your skeletal muscle arteries, and also cerebral. Your brain will get extra blood flow during your sympathetic activation too. It gives you more focus. It's supposed to give you more focus during those times. And then again, in every other area, all the non-essential organs are going to vasoconstrict to decrease blood flow to those areas. One slight clinical application is that nicotine actually is going to mimic these effects as well. You're going to have an increased blood flow to your heart and to your skeletal muscle and to your brain. So you may get like a really quick instance of focus when you inhale or have a patch of nicotine. But the thing is, that's very short-lived. And so you have to keep taking that nicotine more and more to get that same kind of effect, which is why nicotine is so addictive. And nicotine is one of the only chemicals that have a straight shot to the brain. It's one of those ones that can bypass the blood-brain barrier, and it's a very quick effect, which is why it's so attractive to some people who are prone to addiction, and why you get addicted so fast. But any questions on that?
So
It's bad, and it increases your blood pressure overall, puts more pressure on your heart. But yeah.
for did I say alpha receptors?
Mm-hmm. Yeah.
So there's 2 different receptors that do different things during fight or flight, is what you're saying?
Yeah. So the alpha-1 receptors are going to be constricting all the blood vessels in the non-essential areas. We use beta-2 receptors to dilate vessels in the essential areas. And then catecholamines action on the heart muscle is to increase contractility. So do not forget that your sympathetic nervous system has connections on the SA and AV node, but also at the myocardium, at the ventricles as well. And these actually use a different receptor. For increasing contractility, these are actually beta-1 receptors. Now, do I ask you so much about beta-1, beta-2, alpha-1, alpha-2 on exams? No, I don't, but it is part of the curriculum. It may come up on a TEAS exam or something in the future, so just be mindful of that. Yeah?
I have a question about the short-term regulation, the neuroreceptor.
Uh-huh.
So the impulses from the baroreceptors cause decrease in the impulses to the heart.
Uh-huh.
Does it also cause an increase in parasympathetic?
So which part are you talking about? This one right here?
Yeah.
The increase?
Yes.
Okay. So you're asking if,
Does the vasoconstriction just come from just the lowered sympathetic impulses, or does it also?
come from parasympathetic?
Yeah.
So during this time when we're trying to, on here, let me see, increases impulses from the baroreceptor. Oh, because we're trying to slow down the heart. So yeah, so we're going to be, it's going to be more of a parasympathetic activation in this case instead of a sympathetic activation. Yeah. So you're talking about right here? So at the same time that we're decreasing sympathetic impulses, we'll be increasing parasympathetic impulses. Yeah. All right, so more about hormonal control is going to be, this is called the renin-angiotensin-aldosterone pathway. We haven't talked about this in length yet, right? No, okay, so this is the first time I'm going to be talking about this in length. Please know this very well. This is something that's going to come up over and over and over again. We're going to talk about it again when we get to the respiratory system. We'll talk about it again when we get to the kidneys. We'll talk about it again when we get to the very end of fluid balance. This is something that's going to come up over and over and over again throughout the semester. This is how we regulate blood pressure when blood pressure gets too low. So this is whenever you see a diagram like this that has multiple steps that occur, this is a very highly regulated system, and everything has to happen just so in order for the desired effects to occur. So this whole pathway, if you have a decrease in arterial pressure, this inhibits baroreceptors, meaning they're getting less signals because of that drop in pressure. And so that's going to activate our sympathetic nervous system. Anytime we have a drop in blood pressure, our sympathetic nervous system is going to be turned on to speed up the heart to try to compensate for that low pressure. And so sympathetic nervous system gets turned on. What that's going to do is that's going to cause the release of something called renin, okay, from our kidneys. That is a hormone that's released from our kidneys. That renin, what that's going to do is that is going to cause a conversion of a chemical called angiotensinogen. That renin is going to convert angiotensinogen into angiotensin 1. You remember we talked about fibrinogen being an inactive protein, and then it turns into fibrin? The same idea, not the same idea, but anytime you see something ending in inogen, that means it's an inactive form of something. So angiotensinogen, angio meaning related to blood vessels, tension, and pressure. So angiotensinogen is an inactive protein that regulates blood pressure. Right? So angiotensinogen gets converted to angiotensin 1 through this chemical called renin that gets released from the kidneys. And then angiotensin 1 gets converted into angiotensin 2, and that is done by a enzyme called angiotensin converting enzyme, or ACE, and you can call it ACE. This ACE enzyme is actually produced by the lungs. So again, a drop in arterial pressure, baroreceptors detect that change. It turns on our sympathetic nervous system in effort to increase heart rate. That causes the release of renin from the kidneys, which is going to convert angiotensinogen into angiotensin 1. We have this enzyme from the lungs that's going to turn angiotensin 1 into angiotensin 2. And then angiotensin 2 is going to have all these different effects throughout the body in order to increase blood pressure. On the short term, a short-term regulation of blood pressure is going to, and you can see the black line leading down on the right, the short-term regulation is that angiotensin 2 is going to cause vasoconstriction body-wide. But that's just a short-term fix. That's just a temporary fix at the start of this pathway. We're going to have other things that are going to be more of a long-term resolution to that. So again, once we get to that angiotensin 2 is going to target blood vessels body-wide in order to increase resistance. It's going to vasoconstrict them in order to increase resistance, which is going to then increase our overall pressure. Any questions about that?
So the renin activates the angiotensin into
angiotensin 1. Yes, so the renin is going to be facilitating that activation of angiotensinogen into angiotensin 1. Yes. And so then we have other pathways too. One thing to know is when we have vasoconstriction and vasodilation, that's just a short-term fix. That is a short-term regulation. Anytime we make changes to blood volume, so changes to blood volume is going to be a long-term control. It takes longer to happen, but it persists for longer. So how we do that, there's actually a few different pathways to do that, but we'll talk about ADH first. But angiotensin 2, one of the targets is going to be the posterior pituitary. It's going to get the posterior pituitary to increase ADH secretion. So we're going back to hormones. Do not forget your hormones. Angiotensin 2 causes an increase in ADH. You should already know ADH causes more water reabsorption at the kidneys. So more water is being redirected to the blood, which is going to increase blood volume, which increases blood pressure. The more water you put into the blood, the more fluid you put into the blood, it stretches those vessels and increases the pressure. Right? So that's through ADH. Before we get to, I'll go back to that slide here in a second. Another pathway though, angiotensin 2 is going to target the adrenal cortex to get it to secrete more aldosterone, which is going to increase sodium reabsorption at the kidneys. But if you remember, sodium and water are like BFFs. They go everywhere together. So anywhere sodium goes, water is going to follow. So as we reabsorb sodium to the blood, we're also going to be reabsorbing water, which increases blood volume, which increases blood pressure. One new hormone that you haven't learned before, so this would be one to add to your list of your hormone flow chart, is ANP. Atrial natriuretic peptide. Where do you think that's produced? Atrial natriuretic peptide. In the atria. So it's going to be actually produced by the heart. So the atrial natriuretic peptide is an antagonist to hormones that increase blood pressure. And specifically, it's an antagonist to aldosterone. So atrial natriuretic peptide, or ANP, and this is a hormone, so you are free to abbreviate it. I won't expect you to spell out atrial natriuretic peptide, but if you can and you do it correctly, you'll get an extra quarter of a point. But you can call it ANP. So ANP, it is released when blood pressure is too high. It stops sodium reabsorption from happening. Okay, so more of that sodium is going to stay with the urine, which means more water stays with the urine and less is going to the blood, okay, which should decrease blood pressure. So it works against sodium reabsorption in the kidneys and causes vasodilation short term, which is going to decrease blood pressure. So this is going to happen when our blood pressure is too high, and it's going to work against this whole system that we're talking about. Does the opposite.
So the AMP will decrease blood pressure?
While this renin, angiotensin, aldosterone pathway we talk about is how we increase blood pressure. And you're free to call this pathway the RAA pathway, renin, angiotensin, aldosterone pathway. But that angiotensin 2, again, on the short term, it's going to vasoconstrict our vessels. But while that's happening, we're also working on long-term resolutions. So angiotensin 2 causes more ADH, which causes more water reabsorption, higher blood volume, higher blood pressure. It also causes from the adrenal cortex more aldosterone, which means more sodium is reabsorbed, which means more water is reabsorbed, more blood volume, higher blood pressure. The last mechanism that it does to help increase blood pressure is that your thirst mechanism is turned on. So your hypothalamus controls thirst. So angiotensin 2 is going to target your hypothalamus to turn on your thirst mechanism. This should make your salivary glands stop working, or at least slow down a lot, so that your mouth gets dry. And so then hopefully you're listening to your body cues and you're drinking more water. And anytime you drink more water intake means a higher blood volume, which means a higher blood pressure. Yeah.
simultaneously?
No, it's all happening at once because angiotensin 2 is a hormone. So it's circulating throughout the body looking for receptors, and it's going to have receptors at the adrenal cortex, at the posterior pituitary, at the hypothalamus, and at all of our blood vessels. So this is happening all at the same time. These are all 4 different ways that we're going to increase blood pressure.
But like something as simple as drinking water, things like that. So with that,
Well,
first.
you can drink water like that, but it's going to take time for your body to absorb that water and put it into the blood. So all of these different mechanisms are going to help increase blood pressure. But as soon as we get back to normal range, this whole thing turns off. And we can stop making these efforts as soon as your blood pressure regulates.
But I guess where my question here is it all happening like in a specific order? Does one take more time than the other, or?
Well, now some are going to take more time than others.
Okay.
Vasoconstriction happens immediately.
Yeah.
That's our short-term fix. Okay. The thirst mechanism is probably going to be around the second fastest because your mouth is going to get dry. You're going to drink water, and that's going to happen. As far as the other ones go, you're producing hormones. It's going to take time. That hormone has to circulate. It has to bind. Has to cause changes in your urinary physiology, and then blood volume can increase. So those are probably going to be the ones that take the longest. Is the hormonal controls with the kidneys, but it's all happening at the same time.
That makes sense.
Yeah.
Is the like AMP like hormone, is that more of a long-term solution?
It's both actually. So AMP does both long term and short term. On the long term, it's going to cause less sodium reabsorption, so more water stays with the urine, and blood volume is going to decrease, and blood pressure will decrease. But on the short term, it does vasodilation. It does the opposite of what angiotensin 2 does. Any other questions? Okay. At this point, you're not going to have to recreate this entire diagram, but understand what's happening, understand the mechanisms, understand how aldosterone works to decrease blood pressure, know how ADH works to decrease blood pressure, know that when you drink water, you absorb more water and increase blood pressure. And then know that any changes to the diameter of the blood vessels, vasoconstriction or vasodilation, that's more of a short-term response versus blood volume changes are going to be a long-term response. So be able to discuss this, but you don't have to have it completely memorized just yet. We'll get there. Yeah.
For the AMP, well, I know you said it's an antagonist of aldosterone, but what does it do again?
It stops sodium reabsorption. So as your kidneys are making urine, it makes it so that more of the sodium stays with the urine. So more water is going to stay with the urine and not go towards the blood.
Oh,
Yeah. Any other questions? But that answers your question.
Someone who has like constantly high pressure, will they have like high levels of AMP or?
Mm-hmm.
Yeah.
Mm-hmm. Anytime someone has high blood pressure, you're going to have AMP release. All right, so now we're going to talk about renal mechanisms. So how do the kidneys control blood pressure? So the kidneys actually have a direct renal mechanism in order to correct for high blood pressure. So how the kidneys work is that blood flows through the kidneys. The kidneys filter out that blood to make our urine. Okay, so basically blood is flowing through these. What are the type of capillaries that we find at the kidneys? Yes, it's the F. What is the F?
Fenestrated.
Fenestrated. So at the kidneys, we have fenestrated capillaries. When the blood moves into these fenestrated capillaries, it pushes up against those pores, and the fluid that comes out of those pores are going to eventually become your urine. Okay, so there is a direct renal mechanism to correct for high blood pressure. So if you have really high blood pressure flow through these vessels, what that means is more fluid gets pushed out, which means more urine is made, and blood pressure here is actually regulated immediately. Okay? If it's flowing at its regular pace and you have a regular amount of urine coming through, that's the normal pace of urine production. But if you have an increase in blood pressure, that blood is coming through more forcefully, which means more fluid can be released. And that immediately regulates blood pressure, but only at the kidneys. Okay, this is only a local change. This is not going to change blood pressure body-wide. This just changes blood pressure at a local level, just for the kidneys itself. It's really important for kidneys to have regulated blood pressure so that urine is made at a normal pace, and we can get rid of the toxins that we need to get rid of, and make, well, yeah.
So is the medication like furosemide? You know how that like kind of just makes you go pee?
Uh-huh.
To decrease your blood pressure?
Yeah.
Is that like this but more?
I don't know what the mechanism of action is for furosemide. Oh, is it a loop diuretic or osmotic diuretic?
I think it's a loop diuretic.
Let me see. Yeah, so it's a loop diuretic. So all it does is on the loop portion of our tubules in the kidneys, it stops reabsorption from happening. And so more of that, of like your potassium, your sodium, water stays with the urine. And so more water stays with the urine wherever the solutes are. And then you pee out more and you're putting less of that water towards the blood.
Oh, okay.
All right, so any questions about that? This is how the kidneys directly regulate their own blood pressure at a local level. If you have high blood pressure, more fluid is pushed out through fenestrations, so you have more urine, less blood volume, and therefore less blood pressure. Indirect mechanisms for low blood pressure include this pathway we just talked about. Renin is released from the kidneys, and then that causes these conversions to angiotensin 1, angiotensin 2, and then that triggers all these different pathways that will eventually increase blood pressure back to normal. So these are indirect renal mechanisms for low blood pressure. What it means by indirect is that renin gets released, but we don't see the effects of that until way later in this pathway. So it's not the kidneys directly fixing this, but it starts off the process of increasing that blood pressure. Does that make sense? This way is how the kidneys, by their structure, immediately change blood pressure. This is a direct mechanism. Versus indirect, it's a more longer sequential path to get to that increase in blood pressure. All right. Last big thing we're going to talk about today, and then I'll talk a little bit about hypotension, is capillary dynamics. So if you're not awake, slap yourself in the face a little bit and get up, because this is going to be a little bit more difficult than what we've talked about so far. So one thing is a little intro to capillary dynamics and bulk flow. We have slow blood flow through the capillaries for diffusion of nutrients, gases, and bulk flow fluids. So on this capillary bed here, you can see on the arterial side where it's going to come through first, you see arrows going out. On the arterial side of a capillary bed is where we have delivery of oxygen and nutrients. As we move further down the capillary bed, we have changes in pressure, because anytime we move farther away from the heart, we're going to have a decrease in pressure. We have changes in pressure on the other side of that capillary bed where it's starting to transition into veins. And on that side is where we actually pick up the waste products. Any CO2, any other waste products that the cells need to get rid of, the organs need to get rid of, we pick up on the venous side. And then all of that is then returned back to the heart. So we're going to talk about exactly what pressure changes and osmotic changes occur to make this happen, to make things flow out on the arterial side and then flow back in on the venous side. So each day, 20 liters of fluid filters from the capillaries at the arterial end and flows through the interstitial space. Most of that fluid, about 17 liters of that fluid, is reabsorbed on the venous end. So this is not a perfect system. We deliver 20 liters of fluid on one side and only pick up 17 liters of fluid on the other side, which means there's 3 liters of fluid unaccounted for. And that's what our lymphatic system is for. You see this green vessel at the bottom. Our lymphatic system is there to absorb any remaining fluid. Otherwise, if we just had this 3 liters still hanging in the interstitial space, we'd have swelling all over the body, okay? Which is not ideal, obviously. So we have the lymphatic system there to pick up any excess fluid that was not picked up on the other side of that capillary bed.
Was does it do with the fluid? Just like kind
It-
of releases it? Or?
That it goes through lymphatic flow and then gets dumped back into your subclavian veins, which goes back to the heart.
Okay.
We'll get there right after the exam. We'll talk all about the lymphatic system. But does that make sense to everyone so far? Okay. Before we get to the math portion of it, you're going to have to know some definitions. So first we have what's called hydrostatic pressure. Hydrostatic pressure is the pressure exerted by fluid against the capillary wall. How much force is being pushed up against these capillary walls as they're trying to deliver fluid and oxygen nutrients to the organs? It's basically blood pressure. Hydrostatic pressure is essentially blood pressure. How much pressure is being exerted from the inside against the walls? So we have hydrostatic pressure of the capillary. So this is going to be how much pressure is being exerted from inside the capillary outward from blood flow. This is an outward pressure. We also have hydrostatic pressure of the interstitial fluid. This is, and let me show you a picture so this can make a little bit more sense. So hydrostatic pressure of the capillary is going to be as blood is flowing through this capillary, how much pressure is being exerted against the wall. Okay, it's going to be pretty high on the arterial side because we have a higher pressure there, but how much is blood pressure pushing up against the walls? Now, for hydrostatic pressure of the interstitial fluid, which is here, you can see it's 0 here, that is how much pressure is the interstitial fluid applying to the outside of the wall. That is very low. Okay, the reason for that, the blood that's flowing through the capillaries is being directed by our heart and by the smooth muscle of our artery. So it's moving in a very fast pace in one single direction. And so it is applying pressure inside that blood vessel. The interstitial fluid, though, is kind of just floating out there. It's not going in any one direction. There's no pump pumping in any one direction. And so the pressure against the interstitial, or pressure against the wall by the interstitial fluid on the outside is essentially 0. Because again, that fluid is not moving in any one direction. It's kind of still, okay, and doesn't really force any movement against the capillary wall. So compared to the pressure on the inside, the interstitial fluid pressure from the outside is essentially 0. Yeah.
Would that be because you don't want like the fluid coming out of the like from the side to like get pushed back in?
Exactly. So this is how we allow for delivery on the first half of that capillary bed. And we'll talk about the differences in pressure and how that allows that to happen. Osmotic pressure is a pressure created in fluid by protein and other non-diffusible solutes. So osmotic pressure is essentially how much is water being attracted to an area because of the proteins that are there or because of the solutes that are there, the sodium that's there, how much is water being pulled in one direction. So again, essentially it's the attractive force of water towards those solutes. So we have osmotic pressure of the capillary, or capillary osmotic pressure. So how much is water attracted to the capillary where all the solutes are? And then we have osmotic pressure of the interstitial fluid. How much is water attracted to the outside fluid? Now, one thing to remember, what is one chemical or one structure that we find in your intracellular environment, also in the blood plasma, but we do not find in the interstitial space? We talked about those 3 fluid compartments. What's the one thing we don't find in the middle? Protein. Protein is a huge attractive force for water. So if we have protein in the capillary, but little to no protein in the interstitial fluid, water is going to be much more attracted to the capillary than it is going to be to the outside. Does that make sense? Okay. So that's actually going to help determine or help allow fluid to be delivered on one side and then fluid to be picked up on the other side. That's going to be determined by these differences in pressure. All right, so now let's get into some math. So remember, this is going to be, we'll talk about the arterial side first, and then we'll get into the venous side on the other side. All right, so For hydrostatic pressure of the capillary, that is 35 millimeters of mercury. That is an outward pressure. So how we're going to do this is we're going to keep track of the outward pressures and the inward pressures. Outward pressure is going to be the hydrostatic pressure of the capillary. As that blood is moving through the capillary, it is putting a pressure against the capillary wall at about 35 millimeters of mercury. That is an outward pressure. Hydrostatic pressure of the interstitial fluid from the outside to in, that's going to be about 0, because again, the interstitial fluid on the outside of the capillary is not moving in any one direction, and so it doesn't really apply any force to the capillary from the outside. That is an inward pressure, but that inward pressure is about 0. And again, this is my HPC, and this is HPIF. Okay, osmotic pressure of the capillary is about 26 millimeters of mercury. Because of the solutes that are inside the blood, the proteins that are inside the blood, like your albumin, your fibrinogen, and so on, we have about 26 millimeters of mercury forcing fluid in. And this is our osmotic pressure of the capillary. The osmotic pressure of the interstitial fluid going outward, how much is water being attracted to the outside, is actually only 1 millimeter of mercury. Not very much at all, because again, most of the solutes are going to be in the blood, including the protein that we do not see on the outside. So compared to the water attraction to the capillary, to the outside, it's minimal. Only 1 millimeter of mercury. And this is our osmotic pressure of the interstitial fluid. Does everyone have a good understanding of why the pressures are different from each other? Okay. So our outward pressures add up to 36 millimeters of mercury. Our inward pressures are 26 millimeters of mercury. So what's the difference there between in and out? 10 millimeters of mercury difference. Is more of that pressure outward or inward? Outward. So because we have a difference of pressure of 10 millimeters of mercury, and that difference is more towards the out, that allows us to deliver the oxygen and nutrients outward from the capillaries to the organs, to the tissues. Does that make sense? Yes.
So how do the gases go in?
That, we're going to talk about the difference in pressure on the other side and how it allows for that. But everybody okay with how these differences in pressure allow us to deliver oxygen nutrients to the tissues? Okay. Any other questions before I move to the venous side? Okay. Once we get to the venous side, we have a significant drop in pressure, hydrostatic pressure of the capillary. Because remember, as we get farther and farther away from the heart, the pressure is going to drop. Now we're getting to the venous side. Walls are thinner, pressure is lower, and so the hydrostatic pressure of the capillary is only 17 now. So again, we're going to organize our outward pressures and our inward pressures. Our hydrostatic pressure of the capillary is now only 17 millimeters of mercury, because now we're on the venous side. This is our HPC. And then our hydrostatic pressure of the interstitial fluid is still 0. We still don't have any forceful pressure on the capillary from the outside, because that interstitial fluid is not moving in any one direction. So it's still 0 millimeters of mercury for our HPIF. Our osmotic pressure of the capillary is still 26. Okay, we still have most of our solutes and our protein are inside the capillary, inside the blood there. And so our inward pressure from osmotic pressure is still 26. 26 millimeters of mercury. And this is our osmotic pressure of the capillary. Yes, we have just delivered some solutes, so there's theoretically less solutes in the capillary, but it's not significant. It doesn't cause a difference in pressure. Okay, it's still at 26. The attractive force of water is still going to be mostly towards the blood and not towards the interstitial fluid. And so the outward pressure, osmotic pressure, is still going to be only 1. Because again, interstitial fluid lacks solutes compared to the capillaries, lacks protein, so water is not going to be very attracted to the outside of the capillary. Our our outward pressures equal to 18 millimeters of mercury, and our inward pressure now is 26 millimeters of mercury. What is the difference now? 8. 8 is the difference, but now what is the bigger pressure, inward or outward? In. This difference in pressure now is what allows us on the other side to then pick up the waste products. Pick up all the things that the tissues and organs don't want, and then eventually recycle those things, get rid of them.
So the first one is for the arteries?
It's for the arterial side where delivery happens.
Yeah, and are those pressures usually stay the same?
Yes.
Like they're consistent?
This is for a normal, healthy individual. Obviously, if you have high blood pressure, these numbers are going to change slightly. Or if you have vascular damage, the numbers are going to change slightly. But for a average, healthy adult person, this is the numbers that you should see. But yes, this is on the differences in pressure on the arterial side allow an outward delivery of nutrients. That change in difference on the venous side allows for us to bring that fluid back in along with all the waste products. Because remember, we're delivering 20 liters of fluid. We do not want to leave those 23 liters of fluid just out there in an interstitial space. We need to be able to pick up that fluid along with any waste products to keep that continuous blood flow. Does that make sense to everyone? Hopefully I broke it down well enough. So we're going to do a little bit more practice here. So again, our hydrostatic pressure from the capillary is about 35. How much pressure the blood is exerting on the capillary wall. And then one thing I'll mention, the hydrostatic pressure of the interstitial fluid from the outside is 0 under normal conditions. So I just leave that out. It's always going to be 0. It doesn't change that pressure from the outside. But our hydrostatic pressure of the capillary is 35. Our osmotic pressure of the capillary, how much is water attracted to the inside of the capillary, is 26. And then the osmotic pressure, how much water is being attracted to the interstitial fluid, is much less at only 1. So our outward pressures are 36. Our inward pressures are 26. And that gives us a net 10 millimeters of pressure outward. That allows us to deliver oxygen and nutrients on the arterial side. Once we get to the venous side, it's a little bit different. Hydrostatic pressure is going to drop considerably, considering now we're farther away from the heart. Only 17 here. But the osmotic pressures don't change. We're still 26 millimeters of mercury pulling water towards the capillary. Only 1 millimeter of mercury pushing water towards the outside of the capillary. So now our outward pressures equal 18. Our inward pressure is 26. And that gives us a net 8 millimeters of pressure inward in order to pick up that fluid, pick up the waste products, and recycle, get rid of them as we need. Any questions on that? I know it's a lot, so it's going to take some practice going through it. Now, if you can, after you've studied this for a while, if you go put all your notes away and explain this entire thing from beginning to end, then you've mastered it. So that's the goal. The goal is to study something as many times as possible to then again put everything away and explain everything from point A to point B and know what you're talking about. That's the biggest part. It doesn't do much to be able to memorize a script, but you don't really understand what's happening. You have to understand it in order to make all the different connections, because this is going to connect in many different ways throughout the semester. We're going to bring up capillary dynamics again when we get to the urinary system and making urine, because there's going to be some capillary dynamics at play there as well. So it's really important that you understand this at each step of the way. Use your pals, come to office hours, please. Go to tutoring to make sure that you really understand it so that when it comes up again, you're not like, what was she talking about? Hey, you want to really be able to understand it because it is going to apply in many different places. Yes,
If there's edema, is that when there would be like outward pressure on the?
that's what we're talking about next. So when there is a offset to these pressures that cause more pressure out than what can come back in, then you're going to get edema. You're going to get some leftover fluid in the interstitial space. So this is just, again, an overview. Make sure that you know we're delivering oxygen and nutrients on the arterial side. We push out about 20 liters of fluid. Because of the differences in pressure on the other side, that allows us to bring most of that fluid, about 17 of that 20, back in along with any waste products. And then our lymphatic system picks up the extra 3. Now, when that system is out of whack, we can get what's called edema, where that fluid gets trapped in the interstitial space and goes into places it shouldn't. So, edema is when we have an increase in interstitial fluid. And it's an abnormal increase in interstitial fluid. This can be caused by either an increase in outward pressure a decrease in inward pressure or I'll put a star by it because we're not quite there yet. This is going to be talked about more in lymphatic system. When we also have a decrease in drainage by the lymphatic system or lymphatic vessels. So, again, we can have edema if we have an increase in outward pressure. So times when we may have an increase in outward pressure include if you have increased blood pressure overall, or if you have an increase in blood volume for some reason. Anytime you have an increase in blood pressure, that's going to increase that 35 millimeters of mercury, and you're going to end up pushing out more fluid than what your body can pick up. So let's say you have high blood pressure, and on the arterial end, you're able to push out 25 liters of fluid. But at the end of the day, the venous side is only going to be able to pick up 17. Your lymphatic system is only going to be able to pick up 3. So now you have 5 liters of fluid that are unaccounted for, filling up spaces that it shouldn't. Does that make sense? Okay. Also, if you have a decrease in inward pressure. So let's say you had cirrhosis and you're not making the blood proteins that you're supposed to be. You're not making the albumin specifically is what the most important thing is, because albumin is what drives water towards the blood. And so let's say you have cirrhosis and you're not making albumin, and so you're not getting that attractive force of water towards the blood. More of that water, more of that fluid stays on the outside and is not picked up. Okay, because now you're having more of an attractive force to the outside. Okay? And so in that case, you're still going to have edema as well. Okay. Also, if you have a decrease in drainage. So one big example is if you were to have tumor removal on the breast. This is a really good example. If you were to have a tumor removal or a mass removal or maybe even a mastectomy where you remove the entire breasts, what's going to happen is when you remove that tissue, you also remove lymphatic capillaries. That gets removed as well. And so when you have these capillary dynamics and the lymphatic system is supposed to be picking up this extra fluid, but now they're damaged or gone because of breast augmentation or a mastectomy, well, now you don't have those vessels to do that drainage for you. And so a lot of people who have mastectomies or have tumor removals at the breast have a lot of swelling, have to have drainage tubes in order to drain that extra fluid because the lymphatic capillaries are no longer there or they've been damaged. Over time, your lymphatic capillaries can repair, and that drainage should decrease over time, and you should be better at draining from the inside, but that takes time. So some patients will have to wear the drainage tubes and the little sacks to hold it for a while after their breast surgery, just because, again, they've lost that drainage that they should have had before. Okay, any questions about that? Non-graded homework is going over hypertension and hypotension. In your textbook, there is a section on hypertension and hypotension, different types. I want you to, if flashcards are your thing, make flashcards on these different types of hyper and hypotension, or however you want to do it, notes. But I want you guys to work on learning those different types. Also, make sure that you're writing out that negative feedback loop on cardiac output and resistance in response to changes in blood pressure. So again, you won't have to recreate this entire diagram, but be able to understand it. So you should memorize it in some capacity. Also, this is just an overall diagram of all the ways we talked about to increase cardiac output and increase resistance, which increases our blood pressure. So be able to read this entire diagram and understand it. Be able to discuss it. We discussed it all, but it just kind of puts it all together. And then you do have a PLA on circulatory shock.